Alright, welcome back to our next part of the topic of turning effect of forces. Today we'll focus on the principle of moments. But before that, let's just recap what is moments. Moments, remember, is equals to force times distance. This distance must be the perpendicular distance. And for moments itself, there are two directions. One is clockwise, another is anti-clockwise. So let's take note of this formula. So let's find out what is the principle of moments. The principle of moments states that when a body is in equilibrium, the sum of the clockwise moments about a pivot is equal to the sum of the anti-clockwise moments about the same pivot. So this is the same pivot that we are talking about, from the same pivot. So please take note, you must include the last part from the same pivot. So let's take a look at an example. There are two forces here. This is like a seesaw, one force on the left, the other on the right. 4 newtons on the left, 2 newtons on the right. Distance, perpendicular distance away from the pivot. So very clear, very simple. There are two moments here, one clockwise, one anti-clockwise. So let's calculate it using the formula. Taking moments about the pivot, the sum of the clockwise moments. So you ask, this is on which is clockwise, which is anti-clockwise. Remember our clock, our minute hand, it will turn this way. This is what we call as clockwise. So which force will give a clockwise about the pivot here? The pivot is here, the triangle. Which one will give the clockwise? Correct, it's the 2 newtons. So this gives the clockwise. This 4 newtons will cause it to turn in the anti-clockwise. Okay, so once we have this itself, let's do the calculation. Remember, moments is force times distance. So the clockwise moment, take the force, which is 2, times the distance, which is 2, perpendicular distance, remember, 4 newton. For the anti-clockwise here is 4 newtons, and the distance is 1 meter. So if we calculate for the clockwise moment, 2 times 2 will be 4 newtons meter. If we calculate for the anti-clockwise, it's also 4 newtons meters. Can you see something special here? That these moments on both sides, the clockwise and the anti-clockwise, they are balanced. So when they are balanced, we say that the rod is in equilibrium. The rod doesn't turn, is equivalent to 2% on the seesaw, and the seesaw is balanced nicely. Okay, so this is what we call equilibrium, and this is how we use the principle of moments. So please take note here on how I use it. This sentence here and this sentence here, please write it in before you actually do the working. This is like your formula. Okay, next, we mentioned the word equilibrium. What does equilibrium means? Okay, equilibrium means that a system have no net force acting on it. This is when all the forces in the systems are balanced. Second, the resultant moment about any pivot is also zero. So let's summarize. Let's take a look at this diagram just now. For the anti-clockwise moments here, anti-clockwise, sorry, give me a minute. Anti-clockwise, the moments is 4 newtons meter. Okay, remember NM, this is moments. For the clockwise moments, this is also 4 Newton meter. So since the moments of the anti-clockwise is equals to the clockwise moments, then the resultant moment is 0 because they are the same. Okay, now then you ask, Mr. Song, what about the force here that you say is balanced? What about the first point? Okay, 4 newtons go downwards, 2 newtons go downwards. So by right, what is the total force downwards? 4 plus 2, correct? Which is, 6. So the rod should go down with 6 newtons of force, but it did not. Imagine your seesaw. Did the seesaw go down into the ground and dig into the hole? No. The seesaw is there, 6 newtons. It did not go down, it did not move anywhere. Why? Because there is a balance of a force here, which is also 6 newtons. So your total force downwards of 6 newtons is balanced by the total force of 6 newtons upwards. So this means that the whole system is in equilibrium. Okay? All right. Next, in your definition itself, you said the word sum. Sum, let's take a look. See the word here, sum. See the word here, sum. Why do we have the word sum? Simply means that sometimes there's not only one 4 Newton, there's not only one 2 Newton, there can be more here. So there'll be 2 forces giving clockwise, maybe even 3, maybe even 4. There are a lot more forces coming. So what you want to do, sum up all the clockwise moments together, add them all up. That will be onto your clockwise moment side. Okay, similarly for your anti-clockwise. Let's take a look at an example. So this is a very good example. This we can sum now. So exciting, we can sum now. There is a clockwise and there's an anti-clockwise. Which is the clockwise? Remember your clock. I'll draw the clock out here again. The clock here. So this is clockwise. It turns this way. Since it can turn this way, so this is clockwise. This one can turn here. This is clockwise. This is anti-clockwise. This is anti-clockwise. Okay. So first question. What is the sum of the clockwise moments? Okay, so there is this one and this one. So let's calculate. So we take 10 times 0.6y from the pivot. This is the pivot here. Distance, perpendicular distance from the force line of action of the force to the pivot, which is 0.6. Sorry. Okay, 0.6 times 10. So 0.6 times 10. Why? Because this is one pair. Next, let's take a look at the next one. This is 5 newtons. 5 newtons times 1. Mr. Song, why not 0.4? Remember, it must be from the pivot. So from here, we need to add 0.6 plus 0.4. This will give us as 1 meter. Okay, so that's why it's 1 meter here. You do the math, clockwise is 11 Newton meter. Next, let's find the sum of the anti-clockwise. Let me erase all of this. Okay, so I'll remove all the clockwise here so that it's easier for us to see. Let's take a look at the anti-clockwise. So anti-clockwise are the remaining two here on the left, 8 newtons and 2 newtons. So we take 2 times 0.5. So this is the first pair. The second one is 8. 8 times what? 0.5 or 1? 1 because it's from here all the way to the pivot. Perpendicular distance to the pivot. 0.5 plus 0.5. This will give us as 1 meter. So down here also times 1. You do the math. This is 9 Newton meter. So they say, what is the net moment? Net means what is the result of this? One is 11, one is 9. Oh, the moment is not balanced. So there is a net moment of 11 minus 9 newtons meter, which is 2. So is the beam balanced? Answer is no. So long as you have a net moment of 2 Newton meter, the beam will never be balanced. That means when you do a seesaw, one side has more moments, it will swing and then you land downwards. Okay? So which direction will it turn? It always will turn in the direction with the bigger moments. So we look at A and B here. Which one has a bigger moment? 11 or 9? 11. So 11 is clockwise or anti-clockwise? Clockwise. So if it has bigger moments, it will turn clockwise. Okay? Alright, next example. Let's calculate the unknown force F given that the system is equilibrium. So we have a pivot here, P. We have 14614 4 newtons. We know now this is clockwise. We know that this is clockwise. We know that this is anti-clockwise. Okay? There is no number here. But never mind, let's treat this as a number. We put it into the formula, then we do the math. So, taking moments about pivot, remember we have to write this line. Then we write this line, sum of clockwise moment equals sum of anti-clockwise moment. So let's put in numbers. Clockwise first, clockwise is here, 6 and 4. Okay, so 6 times 0.6. Why? Because this is one pair, perpendicular distance, remember? 6 times 0.6 plus 4. 4 times? Is it 0.4? No, remember, must be from the pivot. So it's 0.6 plus 0.4. So this will give us as 1 meter. So this is 1 meter here. You do the math, make sum of the anti-clockwise moment. So anti-clockwise is F, so we take the force F. Don't worry, we just put the alphabet F first. What is the perpendicular distance to the pivot? 0.8. Then we have an equation, very nice. All numbers, only one alphabet F that we do not know. Just do the math, calculate. Punch into the calculator, you get your F as 9.5 newtons. So you need a force of 9.5 newtons to balance up this such that your seesaw will be balanced. Okay, anything more, it will swing one way. Anything less, it will swing the other way. Okay, let's take a look at this example here. Well, Mr. Song, why is the pivot on the extreme left side? This is not a seesaw. Okay, do not worry. This is exactly the same thing. All you need to do, identify the force. Where's the force? There is 125 newtons here, and there's 150 newtons here. So what do we know? Okay, if I have the pivot here, and I exert the force upwards, I'm turning it upwards this way. So remember our clock. This is clockwise. So if this direction is clockwise, this direction will be anti-clockwise. Ah, very good. Do you see the pattern? You can still do it. How about the bottom one? Clockwise. So same thing. Write down, taking the pivots about the pivot. Taking the moments about the pivot. Write down the sum of the anti-clockwise moment equals sum of clockwise moment. Mr. Song, is it okay for me to swap the clockwise and anti-clockwise? Yes, perfectly fine. It's exactly the same thing. Okay, so let's look at the anti-clockwise in this case. Which is anti-clockwise? 25. Why? Okay, right, anti-clockwise. So I take 25. What is the distance? 1 meter all the way to my pivot. Remember my pivot here. It must be a perpendicular distance to my line of action of the force. So 1 meter. Then I take the next one, which is a clockwise. Clockwise is here, 50 newtons. I take my 50 newtons, I times where? 0.5, because from the pivot, 90 degrees, 0.5. You calculate both of them and you realize that the moments for the anti-clockwise is 25 Newton meter. The moments for the clockwise is 25 Newton meter. What does it mean? Yep, this system is balanced. It will not move. Okay? All right, so with that itself, we will wrap up on our explanation for principal movements. Have a great day ahead.